Suppose we're given the following Cobb Douglas production function P of L comma K, where L is the units of labor, K is units of capital, and P of L comma K is total units that can be produced with this labor slash capital combination. Suppose each unit of labor costs $900 and each unit of capital costs $1,800. Also suppose a total of $1,080,000 is available to be invested in capital and labor combined. How many units of labor and capital should be purchased to maximize production subject to the budgetary constraint? And also, what is the maximum number of units of production under the given budgetary conditions? So we want to maximize P of L comma K under the given constraint. Let's write the constraint as an equation. Again, L is the units of labor and K is the units of capital. Labor costs $900 a unit and capital costs $1,800 per unit, which means 900L plus 1,800K must equal the total budget of $1,080,000. Now let's go ahead and simplify this by dividing through by 100. We can use the equivalent constraint 9L plus 18K equals 10,800. And now we'll use the method of Lagrange multipliers to maximize P under this constraint. In general, to use the method of Lagrange multipliers, if we have a function f of x comma y, function f of x comma y is going to be maximized or minimized under the constraint g when the gradient of f is equal to some multiple lambda times the gradient of g, which gives us these first two equations, and the third equation is our constraint g of x comma y equals 0. So in our case, the function f is actually p of l comma k, and then for our constraint g of x comma y, we have g of l comma k, and because our constraint is 9l plus 18k equals 10,800, to have our function equal to 0, we'll subtract 10,800 on both sides, which would give us g of l comma k equals 9l plus 18k minus 10,800 equals 0. Which means our system of equations are going to be the partial of p with respect to L equals lambda times the partial of g with respect to L. Then we'll have the partial of p with respect to k equals lambda times the partial of g with respect to k. Then of course we'll have our constraint g of L comma k equals 0. So let's go ahead and find our partial derivatives. To find the partial of p with respect to L, we'll treat k as a constant, so we're going to multiply by 0.9. 30 times 0.9 is 27. And we have L raised to the power of 0.9 minus 1, that's negative 0.1, times k to the 0.1 equals lambda times the partial of g with respect to L. So we'll treat k as a constant, so the partial with respect to L would just be 9, so times 9. And now for our second equation, we have the partial of p with respect to k. So we differentiate here with respect to k, treating L as a constant. So we'll multiply by 1/10. 30 times 1/10 would be 3. L to the 0.9, k to the 0.1 minus 1, that'd be negative 0.9, equals lambda, times the partial of g with respect to k. So we're treating L as a constant, so the partial with respect to k would just be 18. And of course, g of L comma k equals 0 is going to be 9L plus 18k minus 10,800 equals 0. So now we need to solve this as a system of equations. So let's go ahead and solve these first two equations for lambda. So for the first equation, we would divide both sides by 9. So we'd have lambda equals 27 L to the negative 0.1 k to the positive 0.1 divided by 9. And here we'd have lambda equals 3L to the 0.9 k to the negative 0.9 divided by 18. Now because both of these expressions are equal to lambda, we can set them equal to each other and solve to determine a relationship between L and K. When we do this though, let's make the exponents positive, so we'll move L to the negative 0.1 down to the denominator, as well as K to the negative 0.9. So this would give us the equation 27 k to the 0.1 over, we still have a 9, and then we'd have L to the positive 0.1 equals, here we'd have 3 L to the 0.9 divided by 18, and then we'd have k to the positive 0.9. Again, this is true because both of these are equal to lambda. And now we'll cross multiply to determine the relationship between L and k, which means this product must equal this product. So we'd have 27 k to the 0.1 times 18 k to the 0.9 must equal 9 L to the 0.1 times 3 L to the 0.9. 27 times 18 is equal to 486. Then k to the 0.1 times k to the 0.9 would be equal to just k. Remember, we'd be adding the exponents. 0.1 times 0.9 is equal to 1, so we just have k to the first. Equals, on the right, 9 times 3 is 27. And we have L to the 0.1 times L to the 0.9, which would be just L to the first, or just L. So to solve this equation for L, we'll divide both sides by 27, which gives us L equals 486k divided by 27 would be equal to 18k. So now that we know that L is equal to 18k, what we're going to do is substitute 18k for L in our constraint, which will give us one equation and one variable, which will allow us to find k as well as L. Let's do this on the next slide. Again, we know L equals 18k. We also know the constraint is 9L plus 18k minus 10,800 must equal 0. So if we substitute 18k for L, we have 9 times 18k plus 18k equals 10,800. Well, 9 times 18 is equal to 162. So we have 162k plus 18k, which equals 180k. Dividing both sides by 180, we have k equals 60. Well, now we know k equals 60, we know L equals 18k, we know that L equals 18 times 60, which equals 1080. Remember, L equals the units of labor, and k is equal to the units of capital. So going back to our question, we're asked how many units of labor and capital should be purchased to maximize production subject to the budgetary constraints. So we know the units of labor L is equal to 1080, and the units of capital K is equal to 60. So now to find the maximum number of units of production under the given budgetary constraints, we need to substitute these values in for L and K into our function P. So let's go ahead and do this. So we'd have P of 1080, 60, which would be equal to 30 times 1080 raised to the 0.9 times 60 raised to the power of 0.1. So going to the calculator, we have 30 times 1080 raised to the power of 0.9, right arrow, open parenthesis 60, close parenthesis, raised to the power of 0.1. Rounding to the nearest unit and rounding down, we'd have 24,267. Which means, under these constraints, the maximum production, again, is 24,267 units. Before we go, though, let's take a look at what's happening graphically. We're going to graph the level curves for P of L, K, as well as the constraint G of L, K. So we see the level curves of P and G graphed here in blue and green. And these two vectors here, the black vector and the red vector, are the gradient of P and the gradient of G. Notice how when the level curves are tangent to one another, both the gradient of P and the gradient of G are multiples of one another, which is the whole idea behind the method of Lagrange multipliers. So this point here is the point where the production is maximized under the given constraints. I hope you found this helpful.